In this lab session, we'll be taking the combinational logic design skills that we've built up over the past several weeks and apply them to a particular use case to drive the 7-segment displays on our hardware. Before we can do this, however, we need a recap of how numbers work in digital systems, as well as to focus on a new number form, binary coded decimal. In our digital electronics education over the past couple of years, we've learnt that we can represent numbers in all sorts of different ways. These so-called number forms allow us to display a number in the manner best fit for purpose, depending on the context in which they're being used. However, a lot of the time we're only really changing the way we look at a number. Displaying numbers in binary, hex, decimal or octal representations doesn't actually change the way that they're stored in a digital system. At a fundamental level, they're still just binary numbers. However, what these binary digits represent depend on the number's form. Take this binary value for example. In a standard integer representation, each digit represents a power of 2, but as we move towards more complex number forms, this isn't always the case. Binary integers can be signed or unsigned, and if they are signed, whether they're represented in a sign and magnitude, 1's complement or 2's complement format will completely change the number this value represents. We can use binary to represent fractional numbers as well, but even then we've got the option of fixed or floating point, not to mention the matter of signed and unsigned on top of that. We haven't even begun to consider the idea that as this number is stored over 2 bytes, we'll need to take into account the way in which it's stored. We've assumed that it's a 16-bit value, but what if it was actually 13-bit left justified? What if it's stored in Lituendian and the bytes are out of order? The majority of modules we've written over the past few weeks have been specifically for unsigned integers of a fixed width. If we tried passing signed floating point values to them, our answers wouldn't be anything like we're expecting. For this reason, the documentation for IP cores and other digital designs will always specify what number form it uses, as the logic will have been designed with that particular form in mind. So why would we ever want to use all these different representations? Wouldn't it make sense to standardize? Well, there are some common standards that we can use, but they aren't suited for every given situation. Each number form has its own particular use case and is well suited to a particular task. Some forms are more common than others, but even the more obscure forms have a reason for being. We're going to take a look at a specific number form and its use case in this lab session, binary coded decimal. Binary coded decimal is a system in which a 4-bit binary value is assigned to each decimal digit as opposed to its value. For example, instead of representing the decimal 517 as this 10-bit value, we instead represent it as 3 4-bit parts, each representing 1 digit. These 3 parts are then brought together to create a single 12-bit BCD value. This creates a linear correlation between decimal and binary units. For every increase in a power of 10, 4 extra binary units are required, allowing for a more direct representation of decimal numbers in binary. But why would we ever want to use BCD? Well, in electronic systems, we often want to display numbers to the outside world. Binary is obviously not the best representation to use, not many people understand it, let alone can interpret it quickly. We're far better off using decimal, so we need a fast way to convert between the two. We may have physical hardware to represent each digit, something like a 7-segment display or a fixed LCD, so we can use BCD to easily drive that hardware. The conversion process from straight binary to decimal is actually quite tricky, particularly as a digital circuit. We cross powers of 10 boundaries without a linear increase in binary units, so it's hard to compare the two. Using BCD simplifies this process, although with a significant amount of wastage. The maximum value of 9 is represented by 1001, and therefore everything from 1010 to 1111 is useless. So how do we convert from binary to BCD? Well, there are 2 ways. We can either use an algorithm known as double dabble to take a binary value of any size and convert it, or we can take a fixed width binary input and derive a Boolean expression to generate the output. The double dabble algorithm is obviously more robust as we can plug any binary value in and generate a BCD output, but it requires a much higher level of behavioral Verilog than we currently have to implement, so we'll take the simpler route. We'll determine Boolean expressions for the converter, and then it will be up to you to implement these in Verilog, using the continuous assignment skills you'll learn in this lab session. To keep things at least relatively simple, we'll stick to a 4-bit binary input. Any larger than this and our truth tables will get massive. 4 bits will allow us to display values from 0 to 15 in BCD, which requires an 8-bit output. From this information, we can start to build our truth table. We need 4 bits for input, 8 bits for output, and we'll stick a counter in as well so we can keep track of the decimal representation. For the first 10 values, the BCD output simply follows the binary input. But when we reach the decimal value of 10, this first 4-bit chunk resets to 0 to represent the 0, and the second chunk increases by 1 to represent the 1 in the tens unit. We then begin to count up in the first chunk again. Once we've filled our table, we need to create k-maps for each output to derive a set of Boolean expressions to build our circuit with. We'll work our way through each k-map and derive a Boolean expression. Once we reach the last 3 outputs, we can see that there isn't actually anything to drive them, so we can drop them all together. This leaves us with 5 Boolean expressions. We can use these expressions to create a Verilog module to convert a 4-bit unsigned binary number into binary coded decimal. Later on in this lab session, we'll use this converter to drive the 7-segment displays on our board.